Um, so do that. I don't remember, do we have a deadline for that? Is it end of the quarter?
Yes, I think it's the last day of finals week.
Okay. Does anybody have any questions about the HMM lab that we started on Thursday? Folks, is it too recent to really dig into that? Do people have any questions? Okay. I'll take more questions on Thursday, I guess, about that. And for today, I have to run to deal with a kid thing shortly after class. So in my ideal world, I'd be walking out of here at like 2:45. So I envision kind of a shorter lecture. And if you have any questions or want to talk about projects, etc., I'm happy to do that. But maybe Thursday might be a better day. Okay. Today, I thought I would kind of give a crash course talking about model diagnostics and model selection, especially focused on time series models. And this is all material that I think is probably useful for thinking about including in your project write-ups. A lot of the diagnostic stuff is kind of, I guess there's one more logistical thing too, is that I've been having some HTML issues and GitHub is not letting me push stuff right now or putting the slides up. So this is just something that I have local, and I'll make sure to try to push this all the slides up tonight so people can have access to those as well. So the model diagnostics, this is an important part of any modeling exercise. People who have written papers have probably gone through this process. I think that this is some of these diagnostics are things that are just kind of an essential step of any analysis. And so for the purposes of the lab write-up or any paper that you would use this material for, I think that this is the kind of plots and diagnostics that you'd include in supplemental information. So we'll kind of walk through some diagnostics. We will talk about some different approaches for model selection with time series and some wrinkles that the time series introduce. We'll talk about cross-validation and then talk a little bit about forecast performance and how we might want to quantify that and what are some different trade-offs. Today, so we'll be talking about all this stuff in a time series context. On Thursday, we'll be switching gears a little bit and talking about spatial and spatiotemporal models, especially for the 3 or 4 people in the class who are kind of working on spatial related things for their projects. We'll be talking about extensions of the diagnostics and things like cross-validation, how we might want to think about that in a spatial setting when we also have this time dimension, but also the 2D spatial stuff. Okay, so this is all a review at this point, and this is one of the fun things fun HTML things that's not working for me right now. But basically, we have our observation equation and our state equation that makes kind of the univariate state space model that we've talked about, at great depth at this point. Whether we're working with DFAs or Mars models, everybody's seen this, where the x's represent our states of nature that are hidden, and our y's represent our observations. And then we have some observation error and some process variation and process error on top of that too. Okay, so what's complicated about state space models is that if we, let's back up a slide. If we think about our models here, we have 2 models. And so unlike linear regression, where we have, say, one set of residuals, with state space models, we can have 2 or more sets of different types of residuals. We can have one in this case for our observation equation, relating like how closely our observations match our underlying states of nature, the x's. And then we have a second set of residuals for our state equation, which kind of represents how well does our prediction of the state of nature at time t. So the prediction comes from the x at t-1 times maybe some coefficient plus u. This gives us our total prediction. How well does this prediction match the actual expectation of x of t? So we have 2 kinds of residuals in the state space model context. And we can get them from in the Mars package or other state space model software. We can get them and we'll call them the model residuals, which relates our observations y to the expected value of y at time t. That really represents how well those model predictions correspond to the observations. And then we have a state residuals, which represent how well the predictions of the state at time t actually match up with the estimated version of the state at time t. And it's hard because neither of these things is really observed, right? So that's all coming from model output and from the random effects. There's no real right way to go about kind of working through this, but I think for the purposes of writing a paper or your final presentation or the project, this is kind of how I would think about going through this and thinking about this in a time series setting. And we'll kind of walk through each of these steps. So I think for any of these kinds of analyses, state space models, a basic plot that you would want to do is plot residuals versus time on the x-axis. So anybody, from basic stats, that's a pretty common plot. And the second thing we'd want to do is look for any correlation in those residuals. And so the correlations are, they can be looked at using the standard statistics, the ACF, PACF that Mark talked about earlier in the class. Some folks have already gone down the road of generating QQ plots, thinking about normality of residuals. This is a great test. And what's great about this approach, with QQ plots especially, is that it's pretty robust to the kind of family that we're working with. And so if we're working with the kinds of GAMs that I was introducing for time series models last week, QQ plots are just as appropriate for those kinds of models as they are for maybe the kinds of output that we generate from Mars, where our residuals, both our process and our observation error residuals, are approximately normally distributed. And then the last step, kind of optional, if you really wanted to, you can apply any of the common tests that are used to evaluate statistical kind of support for normality assumptions. And so these are all in R. I'm not going to talk about them today. And they're generally a step that I kind of skip. And the reason I would skip that step is that if we have large sample sizes and I test a lot of the responses that I work with from fisheries or ecology, I think that it's often the case that I work with distributions that might have a slightly heavy tail or maybe slightly asymmetric. So they generally would fail some of these tests. So I don't think it's necessarily, it's not because the distributions are horribly skewed. It's just because they might have long tails, maybe, and better approximated with a student t distribution, but probably a step that you can choose on your own whether that's something that's important. Okay, so for anybody who's got a lot of modeling expertise under their belt, you probably have heard of the Dharma package in R. It's really great. It has all kinds of built-in diagnostics for dealing with residuals. Unfortunately, it's not compatible with all R packages, and Mars is one of the packages that is difficult to kind of crosswalk between Dharma and Mars. But the residual checks in Dharma are pretty straightforward, and we can basically do our own equivalents. So just to kind of illustrate this workflow, this is a temperature of kind of global ocean temperature anomalies. It's a long time series. It's part of the Shumway and Stauffer R book, and so this is just a continuous time series where the time points correspond to years. There's about 150 or 170 years in the time series. And so if we wanted to kind of fit one of the most simple kinds of state space models to this data, we could just pass this time series object to the Mars function. And this is going to be estimating, of course, process variance, an observation variance, an initial state x naught, and a trend or bias, this u parameter. So what kinds of residuals can we get out of Mars, and how do we get them? there's a few different functions you can call to get kind of the same thing. You can call the residuals function by itself, and that will return a tidy object that includes several of these kinds of residuals. We can be a little bit more explicit, like I'm doing here, and we use this Mars residuals function. So we pass in our fitted object, in that case, the univariate Mars fit that I fit on the last screen. And then we have to specify what kind of residual that we're going to generate. And so Eli has done a lot of work, especially 10, 12 years ago, kind of deriving how to generate these various residuals for the kind of the Mars family of models. There's 3 different kinds here. So the first, and kind of the one we'll focus on today, is specified by specifying that our type is little t, big T, and that is the residuals, so our state residuals and our model residuals conditioned on the entire time series in that our data vector y. There's a few different flavors of this where we can specify 1 step ahead residuals, and so that's the residuals, again, the model or the state residuals that are conditioned on all of the data for each time point in your vector. It's conditioned on all of the data up to that time, right before that time point, so up to t-1. And then the similar variant of that are contemporaneous residuals, which are the same thing, where for each time step in our data vector y, we're going to be looking at the residuals using all observations y up to that time step. Okay, so the Mars residuals includes a bunch of other arguments that you can turn on and off. By default, these residuals are not normalized, but if you wanted to make some of those comparisons, again, back to the Dharma package, you can normalize them and create standardized residuals that way. Okay, so step 1, again, is going to be to plot our model residuals. When we call this residuals function, as I was saying, we get this kind of tidy object out of it, and we can plot both of these kinds of residuals simultaneously. So the first, in pink or red, is the state residuals, and the blue represents our observation residuals. And the kinds of things we want to look for here are, is there a trend or is there clumpiness in either of these time series? In general, I think that just by squinting, I don't think there's much of a trend. I think if anything, you can think about changes in the mean or changes in the variance. And when I look at the time series of the red dots, it seems like maybe at the beginning of the time series, they have a distribution maybe between minus 0.5 and 0.5. And this variability seems to kind of shrink in this middle section here. So we haven't talked about it in the context of this class, but I think one thing you could do for this kind of model, if this was really, really a problem for you, and I don't think this is a problem, if it was really a problem that you wanted to fix, or your change in the variance was much more extreme, something you could do is go down the road of fitting models that have time-varying variability. So those models are a little bit more data hungry to estimate. We don't necessarily always estimate changes in the variability per time step, but you could estimate, say, a smoother relationship of that variability through time. Going back to our original data, why does that kind of mesh with what's happening in the data? I think it kind of does. It does seem like at the beginning of the time series here, the variability, at least the first half, the variability in these anomalies seems to be greater, as opposed to the kind of this middle section here, where we have these rapidly increasing temperatures seem to be associated with a dampened variability year to year. Yeah, Mark.
In a situation like that, I mean, is it worthwhile to think about like the temperature data? Presumably that's not the same form of sensor.
Yeah. Yeah, right, because this is probably changing. The inputs used to generate this time series are probably changing over time. Yeah, and so you'd expect, like, there's no satellites back here, so I think that I don't know where that data is coming from, whether that's raw observations or what. But yeah, it'd probably be worth digging into that data a bit more to figure out why the variability is changing. Okay, so, and I guess if you see different patterns here, whether you see patterns in the observation model or the process model, it's really going to send you down a fork of how you want to deal with, or like how to compensate for that in your model. Do you want to change, if you see a pattern or trend in the observation model in blue, it probably means that you need to adjust your observation error model. Maybe that's changing the R matrix. Maybe it's including a covariate in your observation model. Or if you see something that's happening in your process model, like I was talking about in the red or pink, it maybe means that you need to account for something, either a covariate, maybe there's an autoregressive feature that you need to include that's not already in there. But there's some complexity in the model that you're not picking up that you need to include to try to account for or try to minimize the problematic pattern. Okay, so moving on, step 2, like Mark talked about early in the time series, or early in the class, when we apply the ACF and PACF to raw time series data, we're looking for kind of autocorrelation and dependency. And we can do that same thing with residuals. And so in this case, I am taking only the model residuals. So I mean, yes, you do want to do this for the state residuals too, but for just the purpose of this example, we'll only focus on the model residuals. So the model residuals, we apply the ACF function just as we did before. Maybe there's this problem at like lag 2, but I think it's probably, most of this looks pretty well behaved and there doesn't seem to be a really strong pattern. Similarly, with the PACF plot, again, remember we're talking about the model residuals here, and the PACF2, maybe this is a problem, and this value at like lag 2, and maybe what that represents is that instead of this model being this AR1 model where x of t is a function of x of t minus 1 times some coefficient b, maybe this means that there's, in this temperature time series, that there's like a 2-order lag that we're not including, that we need to be including with a second, kind of a higher order AR process. So that might be one way to fix this kind of problem, if this was something that was really concerning to you. Okay, step 3 is talking about normality checks. So QQ plots represent basically points that fall basically right on the line represent kind of our expectations under normal distributions. And when we see problems, it's often occurring at the tails. So like this high end up here actually looks pretty good in this example. We only have maybe like 1, 2, or 3 points that are falling off. Down here, maybe the low values are a little bit worse, but there's maybe only 10 plots or something like that. So I think that this is not terrible. I think that some of you that are working with QQ plots for your projects are seeing far worse, and so I think that this is probably totally fine. Again, this is somewhat subjective too. There's no real test, but this kind of plot is kind of a good diagnostic to include. That I would certainly include in your project write-up, and it's a good diagnostic in any paper, whether we're dealing with time series data or spatial stuff. Histogram of model residuals. So again, what we're looking for is that things are quasi-normal. In this case, we don't want to see a big bimodal distribution or a lot of skew, which would indicate that something is off. So again, this is not a test. It's really a subjective kind of test, kind of diagnostic or tool that you can really evaluate visually. Okay, so that example with the temperature data, that's univariate time series. And all of those diagnostics that I talked about are applicable to any of the univariate time series models. I think one other extension that we might want to think about when we're dealing with multiple time series, like a Mars model, like the harbor seal data that we've worked with a lot in this class has multiple time series. One other diagnostic that we probably want to look at is looking at whether our state residuals or whether our observation residuals are correlated across locations, across time series. And so what I mean by that is when we generate our vector of residuals by time, we could collapse that into a matrix where we had time on the rows and each time series across the columns, where the values of that were our residuals. And then we could simply calculate a correlation matrix across that. What we don't want to see is that there's strong correlations, either large positive or large negative, between time series, which would indicate something, again, a feature that wasn't included in our model that should be there. So an example of this, or like where this might occur and how to fix it, might be if we take our data set of 12 seal populations coastwide and we fit a simple Mars model, maybe the Mars model that I already showed, where we've got a single trend for all 12 populations and single observation and process variances. If we fit that model to all 12 time series, there's going to be some populations that are growing faster than others and some populations that grow slower than others. And because of that difference, when we look at the residuals, some of those residuals are going to have a positive skew and some are going to have a negative skew. And so some of the ones that are doing better than expected might be correlated with one another, where the ones that are doing worse might be also correlated with one another. So the fix for that kind of thing might be that we need to include population or time series specific trend parameters to kind of basically detrend the data and make those residuals less correlated. So I think that this is a kind of thing where if you see that, or if you do that kind of diagnostic, you see that your residuals across time series are correlated. Again, it's a feature that is not included in your model that probably should be there. Again, it also depends on this fork about whether that kind of pattern is occurring in the observation model or the process model. Okay, so that's enough about residuals diagnostics. Now we'll talk about kind of how good our models and what we might do to compare them. This is obviously, I think that everybody's doing this. We might have, instead of building a single model, we're going to be building several, and we want to have some kind of comparison about to kind of justify our inclusion of certain covariates or model structures. And there's a lot of ways we can compare these models. We can compare them based on their ability to explain the data. So this is fit to the training data. We can compare them solely based on their ability to predict future data, or just in their prediction. So we do in the prediction. We could do in two directions. Obviously, we can do forecasting or we could do hindcasting. So there's no right answer here. This is going to vary totally case by case. It's entirely up to you and kind of your application. So in terms of tools and metrics to calculate this, again, sorry for the HTML screw up. This is going to be, we can start with a simple model. We can just fit a simple regression model to one of the time series from the Harbor Seal data set. So this is just a linear regression. We can see we get a really good fit. Maybe these residuals are probably problematic because we have a cluster of values that are positive above the model prediction. So there's some autocorrelation there. However, the overall model fit, the R squared is great. It's 0.83 or multiple R squared 0.84. So in general, this kind of model fits the data really well. This is going to be frustrating as we go through this with the equations. So I'll have to just interpret. So this regression model has a pretty good sum of squares, or the R squared. But using that as a diagnostic alone, as problematic as anybody as you've taken various stats classes, because the more parameters that we add to that model, we're going to keep getting better and better sum of squares. So there's no cost or penalty there to having too many parameters. Everybody's probably also been exposed to the idea of model selection and kind of Occam's razor. We want to kind of find a model that does two things. We want to both explain the data that we have in hand, and probably also pick a model that has good out-of-sample predictability. This is sort of the classic figure. I think this is originally from Burnham and Anderson's book, but we have this bias variance trade-off where model complexity is basically on the x-axis and the prediction error is on the y-axis. As we increase our model complexity, we're going to be doing a better and better job fitting our data, but we're going to be getting worse and worse out-of-sample predictions. And so I think we can think about going back to last week when I was talking about GAMs and looking at the forecast error as we cranked up the number of basis functions that we were using. So with like 5 basis functions, we had a terrible fit to the training data and a pretty flat prediction in the future with we had really low forecast variance as we went out in the future. But as we cranked up the number of basis functions to, I think it was 20 or 30, all of a sudden we fit the data really well. We could have a perfect fit to the data. The R squared was close to 1. But when we looked at the forecastability of that data, we go into this overfitting stage over here where the model really blows up and the prediction error is basically ballooning. So we want to find a model that's kind of right in the middle here and minimizing both of the bias and the variance. There's a lot of theory in this related to AIC. And so what AIC is doing is it's balancing how well we fitted data against the number of parameters. Again, this is really frustrating. Deviance represents how well, it's twice the negative log likelihood. So deviance is entirely based on fit. And it's going to include a penalty for how many parameters we have. So AIC is becoming widely used, I think, largely because it's really accessible. It's become a default for a lot of these different functions, including time series libraries like forecast. So it's very flexible. It's very accessible, and I think one of the reasons it's accessible is that it's easy to calculate. So if we calculate the deviance, which is minus twice the negative log likelihood, the only other component of AIC is the number of parameters. And the number of parameters is something for for fixed effects models, even the kinds of GAMs that I talked about last week. The number of parameters is often something that we can count on our hands. So it's a discrete integer. It's easy to figure out. Where this gets problematic is when we're applying it to time series data, especially working with state space models. So when we have state space models, the number of parameters no longer becomes something that we can count, right? If we have, or at least in my mind, it's not. We have the number of things that we're estimating becomes a function of, the fixed effects parameters might be our variances. So we might have a process and an observation error variance. We might have a trend, and we might have some autoregressive parameter that the B or beta. So those are parameters that we can count. But in addition to that, we also have these estimated latent states. So our entire vector X is a vector of states that is described by random effects. And the longer that vector X is, the more of those latent states we're estimating. But if we were to take a tool like AIC and apply it to one of these Mars models, we're going to be there's not going to be a penalty for any of that complexity. We're still going to, with AIC, we're still going to be using our 2 variances, the initial state, the trend, and the beta potentially. So 4 to 5 parameters, regardless of how many latent states we're estimating. Okay, so AIC, it's very accessible, as I said, very easy to calculate. We also include it in the Mars library. So all these different packages do this. With AIC, as I said, the penalty is twice the number of parameters. It doesn't change based on our sample size. And one of the things that AIC is trying to do is, generate, basically trying to make predictions from the same underlying process that generated the data that you have in hand. So this works if you have stationary time series, if you have covariates that don't have effects that are changing through time, or models that just have fixed effects. AIC generally works great. With large models and really complex hierarchical models, AIC has a tendency to over-penalize. And so there's a lot of literature on this that we're not going to talk about. So if AIC is over-penalizing, on the other side of the spectrum, we have BIC. And so BIC is this is again super frustrating because the difference between AIC and BIC is that in AIC, our penalty is twice the number of parameters. In BIC, the number of parameters is K, which is the number, or the penalty is K times the natural log of our sample size. So K is the number of parameters, just like with AIC. N is the sample size. N does not go into the AIC calculation at all. And what happens here is that as N goes to infinity, this penalty becomes larger and larger, and BIC will fit simpler and simpler models. So, so on one side of the spectrum, we have AIC over-penalizing. On the other side, as sample sizes increase, BIC will be under-penalizing. In the context of time series literature, I like to think about kind of the AIC-BIC difference also in terms of cross-validation. We'll talk about cross-validation a little bit in a second, but there's been a kind of a resurgence of cross-validation over the last decade. AIC is a pretty good approximation to just straight leave one out cross-validation. So if we have a time series and we leave each point out one at a time, we fit our Mars model to the remaining data points, and then predict the held out data point and repeat that process for each time point. That's leave one out cross-validation. But the AIC calculation is a lot more computationally efficient. Instead of just doing that leave one out cross-validation, we could also think about creating a random number of folds or sets of time series, or sets of points in that time series, and resample those. I guess the benefit of k-fold cross-validation is that instead of, if we have a time series of length 100, we're not going to be having to refit our model 100 times. We can divide our data, say, into 5 folds, and each fold we can leave out one at a time. Repeating the same process where we fit the data to the remaining folds, and do that 5 times instead of 100. So BIC is going to end up approximating that k-fold cross-validation procedure the same way that AIC does for leave one out cross-validation. We have not talked about Bayesian model selection. I'm not really going to talk about it here. The biggest difference here, I think, is that the Bayesian tools have really evolved over the last few decades to deal with this problem of hierarchical models and models with lots of random effects, like the Mars models or these other time series models. So the number of the tools out there is, there's a large number of tools. Leave one out information criterion, or LUIC, is an approximation. It's a Bayesian approximation to this leave one out cross-validation. It's pretty widely used in BRMS and STAN and associated packages. So that's probably the tool that you would want to use if you go down that road. And bridging these two worlds, I think that Jim Thorson has a really great paper from last year where he is kind of rethinking this whole model complexity idea for hierarchical models using something that's been popularized with MGCV. And so I talked about this briefly last week, but with MGCV, we can approximate the number of parameters associated with any of our smooths that we are including with our covariates. And so with the models of the measures of complexity are called EDFs, or effective degrees of freedom. And so the more wiggly our smooth is, the more the more parameters, the more effective parameters that smooth is associated with. And we use effective parameters because these are not parameters that we can count on our hand. These are approximations that describe how wiggly that smooth is. So Jim took the same approach, applying that to models with random effects and hierarchical random effects. And these kinds of this EDF framework has generally been associated with the kinds of Bayesian tools that are out there, not available in the maximum likelihood world. So this EDF concept is brand new. I think that it's really promising for measuring complexity, and I think we haven't yet included it in kind of the Mars universe, but I think that that's something that I'd like to do in the future. Okay, cross-validation. We're really only going to be talking about the k-fold cross-validation and a few variants of that today. As I said, we can do the k-fold cross-validation if we take a data set, 100 time steps, divide it into some small number of partitions, and then for each partition, we hold it out one at a time, looking at how well we can predict the data in that partition using all of the other data available. Okay. In the machine learning world, you'll also see this referred to as like using test and training splits, and we can talk about the same thing here. In Mars, there's a few functions that will help do this. We have some bootstrapping functions with Mars boot, and this is a way to generate, if you want to generate confidence intervals, for example, on parameters in your model. The Mars boot function is a really good way to generate uncertainty. The procedure here is generally, though, for any model that you fit, we want to take that model, predict new data from that, refit our model, and look at how well our model is, or look at the distribution of parameters across these new pseudo data sets. So that's really similar to what goes on in the Bayesian world with posterior predictive checks. We're not going to talk about that today, but there's some parallels, and just be aware that the Mars boot function is out there if you would like to generate that kind of uncertainty. So how does cross-validation, or this k-fold cross-validation, actually work? So this time series, this is a data set, a time series of beaver body temperature. And so this is, they put some temperature logger on a few beavers. This is just one of the beavers that I pulled out of the data set. And this represents time, I think in minutes, maybe over the course of a day. So this is basically the time series. These data points are not equally spaced, obviously. But we can take kind of the, any model that we want to. In this case, I'm going to use a state space model with Mars. That's the first step. We could alternatively use a GAM or anything else that you wanted to use. Second step, we're going to partition the data into the folds, and then we'll do the fit and prediction steps. So in this case, we're just going to brute force this in a loop. There's probably more effective ways to do this, but we'll specify we're going to use 5 partitions. Our partitions, our data points, are randomly assigned to one of those 5 partitions. And then each time through the loop, we're going to be dropping out the data associated with the kth partition, fit the model to the remaining time points, and then make our predictions, and our prediction, the standard error of those predictions from that fitted model. So when we run through this whole loop, at the end of the day, we're going to get a new data set that has predictions and standard errors for each data point in our time series, and those predictions will have come from all other data points in partitions, basically in the other 4 partitions of the data. So this is what it looks like. So our black represents kind of our original observed data. The predicted represents predictions from that, that 5-fold cross-validation. In general, this looks like we get a really good fit, really good agreement between these two. A trade-off here, though, is, that was an example with k equals 5. And so we should decide how large do we want k to be. When we do this, we run into this kind of this bias variance trade-off, where if we have low k, so few partitions, we get larger bias. And so this makes sense because if we have if we have fewer points going into our training set, we're going to have a harder time fitting kind of the out-of-sample data. A lot of the machine learning community recommends partitions in the 5 to 10 range. We could go kind of off the deep end here and go more towards leave one out cross-validation. In the leave one out cross-validation sense, that's great. But for a lot of these time series data sets, it's going to become computationally pretty expensive if we have to refit our Mars model 100 times for each time point in that data set. So this is just an example of what the difference in fits looks like from using 5-fold. So the red lines and predictions represents predictions with k equals 5. I cranked up k to 20 here, which we see in blue. And we see these points basically falling right on top of each other. I don't for this particular application, it doesn't seem to really make a difference whether we use 5-fold or 20-fold. And because the 5-fold was running in a quarter time, it probably makes more sense to use fewer folds. OK, so there's a lot of ways to deal with this in a robust sense. We're not really talking about these other packages today, but there's the Caret package in R that does a lot of this automated time series resampling. For this kind of application, Caret will do something else, which will instead of just assigning the folds one time, as I did with that example, Caret will integrate basically over folds. And so it will run through a large number of sets where with the goal of basically averaging across lots of different combinations of how those folds are assigned so that we get predictions that are really insensitive to the particular choice of folds for a given iteration. So this is done in Caret with this repeated CV thing. There's a bunch of other similar tools in the tidy models universe to do the same thing. Again, though, these are not really compatible with the Mars package, but these kinds of tools are out there if you want to really dive into it. OK. With time series data, so with that Beaver data set, we assigned our folds randomly to one of those 5 folds. A challenge is that we totally ignored any of the temporal order or temporal dependency that might be important for making better predictions. So the alternative to that is kind of different variants of k-fold cross-validation or leave one out cross-validation, where we think about the temporal sequencing and then we do our partitioning, our sampling based on the structure of that time series. So there are a couple flavors of this. We can do kind of leave time out cross-validation, which I'm calling here. And so in this case, we could, if we had several years of data, if we had 10 years of data, and we had a beaver tagged in each year, we could leave, or several beavers tagged in each year. We could iterate through our data set, leaving 1 year at a time, and doing the same procedure. So that would be an example of kind of the leave timeout cross-validation. We could also do another flavor of that, which is called leave future out cross-validation. And so leave future out cross-validation is really popular with forecasting, where if we have a 10-year data set, we can only do our predictions that are forward-looking. And so if we have that 10 years of beavers sampled, we don't necessarily care about using data from the 10th year to predict the temperature of beavers in year 7. We only want to be forward-looking. So we're going to be using data up to year 6 to predict year 7, et cetera. There's a number of other ways this process is basically described. So the LFO-CV, leave feature out cross-validation, also called forward chain cross-validation. But in this case, we can build, for example, 4 folds of our data. We can use data from the first fold, representing the first like 20% of time points, to predict data in the the second 20 to 40 time steps. Then we can do the same thing where the test data from fold 1 becomes part of the training data for fold 2, et cetera. So we keep moving this window through our data set where for each fold we expand the training set, and then we use a new chunk of data for our test set. So how does this work with our kind of Mars model Beaver data set? We just change how we partition our data. So instead of partitioning our data randomly, essentially what this chunk of code is doing is just going to be chunking up our data into 5 parts, and we'll be kind of going through each of those partitions from 2 to 5 and doing our refitting and forecasting. And so this is what it looks like. So what was done here is we kind of fit our model to the chunk in this first chunk to predict data in the second, and then for the next. So that's kind of what these predictions in red look like. For the next iteration, we expand our training data set to be basically the first and second partition to predict what's going on in the third. And as we walk through this, we can kind of see that makes sense. If we just draw a straight line through the data, for example, this third partition, that basically represents the mean of that trend. And the same is true as we go through these other ones. What we want to see in this kind of process is that the confidence, the uncertainty intervals are generally decreasing as we're adding more data. I don't think that's exactly the case here, in part because this time series is pretty non-stationary. We have a trend that's changing over time. This temperature time series is basically increasing. And there's some weird, funny patterns in this latter half of the time series that aren't there in the first half. Okay. Again, I'm going to skip over this, not talking about Bayesian cross-validation. We will talk about prediction and forecasting and how we want to quantify kind of the performance of these different approaches. As I talked about with the GAMs last week, anytime we do these forecasts, whether we're using Mars models or ARIMA models or GAMs, we're going to be generating our forecasts, and there's going to be uncertainty here that's increasing. And the further that we move away from data, the more uncertain we are. So we're going to get some increase, some expansion of that prediction error the further we go in the future. And the rate of that is going to really depend on what kind of model we're using. Okay, so how do we want to quantify forecast performance? There's a few different ways we can do this. Most of the versions of this that I'll talk about today are based on thinking about prediction accuracy. And so one of the most common approaches for this is mean squared error or root mean squared error. And this represents how well, how basically the difference between our predictions and the observations. There are a few papers out there that have kind of, will be fixed. But basically, what I would like to say, with this slide is that the MSE concept can kind of be rewritten to think about the variance or the variance squared here of our predictions, the estimated values of X, plus the bias of those predictions, which is really similar to what AIC is trying to do. AIC, remember, is trying to minimize the bias and variance, and lower MSE, lower root mean squared error is better. And so if we can rethink about MSE in terms of this bias variance trade-off, and we want to minimize MSE, it's really similar to what AIC is doing with minimizing the bias variance trade-off. Okay, so MSE and all of its variants can be calculated on single data points, entire time series, only the future forecasts. And so this, again, is very going to be context dependent. If we're doing forecasting and predicting 5 steps ahead, another decision will be, do we want to weight each of those time steps equally? Number one. Number two, do we care about including all 5 time steps in the prediction, or do we just care about the final ultimate value of that forecast? So do we just want to forecast 5 steps ahead and evaluate the fifth forecast year of data against truth, or do we just care about the trend that our model took to get there? So that's, again, there's no right or wrong. This is, again, something that you just need to decide as you're setting up this kind of process. Lots of variants of root mean squared error out there. Other kind of things that are out there that are similar are mean absolute error and median absolute error. This is the root mean squared error is going to be putting, because we are squaring that error term, we're putting a quadratic penalty on that error, versus with a mean absolute error, for example, because we're not squaring, it's going to be just a linear effect. And so the root mean squared error is going to be putting a harsher penalty on values that are far from our predictions compared to mean absolute error, where that penalty is going to become linear. Another consideration to think about in quantifying performance is scale. This is really important when you're considering time series that have maybe 2 different levels. It's rarely the case when you're dealing with it for a single time series. But for this kind of application, where we might have a time series with abundance of a species from 2 different populations, if we were to use a tool like root mean squared error for this application, and we had model predictions, whatever's going on with population 1, this higher time series, that's going to have a lot more weight just based on the scale alone. That's going to have a lot more weight on our total root mean squared error compared to whatever's going on with population 2. So for that reason, people adopt what are called these scale independent measures of performance. What this examples of this, these scale independent measures are things like percent error or median absolute percent error. Percent error is just taking our error between the observed and predicted. So in the state space model, this would be y at time t minus x at time t would be the model error divided by our data, divided by that, which is, so it's normalized by the data so it's on a scale from 0 to 1, and then we multiply it by 100 to get it to be on a scale from 0 to 100. So that's all well and good. It works well. These are scale invariant, so we can compare 2 time series that have really different values of really different levels, values of y, because we're normalizing by the corresponding y from each at time t. Challenges with this kind of approach are that they have kind of this funny effect where they put higher penalties on larger positive values than smaller values, and so I don't see the percent error statistics used as much as like the mean squared error, root mean squared error. The other weird thing is that when y is 0, if we're dividing by y is 0 to kind of normalize our time series, this thing becomes undefined. So obviously it doesn't work very well. But there's a long discussion of kind of percent error and these other tools in this paper by Rob Heinemann in 2006. The last family of these are called scaled error statistics, and so this is a family of this absolute scaled error, or MACE, and this is probably the worst one to talk through when HTML is not rendering correctly. But basically what's happening here is we're going to be comparing the error from our model. Again, the y sub t minus x sub t. We're looking at our average error from the model, and it's scaled, instead of being scaled by y, it's scaled by the predictions that we might get if we were using simply a random walk model to make the predictions. And so the predictions, remember, from a random walk, if we're doing forecasting, the predictions at time t are going to be where we were at time t minus 1. And so, and similarly, if we were to do that for 4 or 5 time steps, we could take all of those one step ahead random walk predictions and then average them. And so that's what's going on in the denominator of the equation there. And the top represents the kind of the model predictions. And so this MACE statistic is one of the more commonly used things for time series out there. We are going to be using it to just compare values against a random walk. We want to minimize it like we are with most of these other error-associated metrics. And so values less than 1 indicate better performance than random walks. Earlier in the time series class, Eli was talking about a kind of a meta-analysis that we had taken on 10, 12 years ago. And we looked at I don't know, 300 or 400 or 500 different time series and a bunch of different models using Mars models and GAMs and a lot of other kinds of models. And the outcome of that paper, so we used MACE in kind of validating different models' performance and looking at the performance across different taxa and time series. And for most of these models, we were getting statistics, values here for MACE that were greater than 1, indicating that even though we're using these fancy models, state space models, or models like GAMs that include nonlinear structures, we were in fact doing no better than a random walk, and that the best forecast was where we were at the previous time step. Okay, so to implement this in R, there's a lot of different ways you can do this. The forecast library, and now it's forecast is kind of being also replaced with the Fable library. But with forecast, we can take our time series object, we can fit our model, generate the forecast really easily. And part of the forecast package is this accuracy function. And if we have a forecasted object, we can pass it into accuracy, and it will generate automatically a lot of these statistics that I talked about today. So it will generate root mean squared error, it will generate mean absolute error, MACE, all of this stuff for that test set. So these are all statistics that you can calculate yourself. They're fairly easy to do. Then this is just kind of there if you need it as a kind of a check against your code. Okay, talk about that. The last thing I want to talk about today are all of the metrics that I talked about, MACE and root mean squared error and the percent error statistics. Those are all measures of accuracy, because we're really concerned with how well do our predictions or forecasts match our data. That's great, and I think what we don't do is minimize that. And if we use any of those statistics, we'll often find models that are that perform really well. One limitation of that approach, though, is that we're not at all concerned with uncertainty of those predictions. And so because of that, there have been a number of other approaches out there. There's been a lot of this work. David Draper has been working on this for a few decades, but scoring or log scoring has become popular as an alternative metric for calculating kind of model performance. And the origin of this too is also kind of the Bayesian world, but there's several good R packages for doing this. The scoring and log scoring names are kind of jargony. Essentially what they mean, though, is the out of sample log likelihood prediction. So instead of just calculating a measure of accuracy based on how well does our observation match our prediction, we are going to be evaluating how well the prediction and the prediction standard error matches our observation. Okay, so just to, I don't have any equations for this because it's just based on likelihood, but this is essentially the black curve here would represent a normal likelihood function. And so you could do this with the d-norm function evaluated across a range of x values. The height of this curve is just going to be the likelihood, the log likelihood from that d-norm function. And we can think about evaluating that likelihood at our red point, at our kind of our location of our observation. So location of our observation with a red line. In this case, this is a not great example because in reality, it's often the case that our black curve, the bell curve, would be optimized right at our observation. That would be a model that fit the data really well and had really good accuracy, right? Because the most likely prediction was also the location of our observation. Here we see that there's some small bias here because these two are not perfectly matched up. Okay, so the difference between this approach and the root mean squared error approach is instead of just considering the distance between our prediction and our observation, we also are thinking about how, across our likelihood, how wide is this curve? Okay, so we could take this and we could compare several models now. And so our black curve represents the same curve that I showed on the previous slide. This is just rescaled because of the different y-axis. But we have our same observation as the red line. We see the same, this black curve has some bias, but it has low precision, right? Because it has lower uncertainty kind of around our prediction. Compared to model 2 now, which is in kind of the blue line. So this thing has a really good prediction, falling right on our observation, but the tails of this blue line are really wide. And so in this case, we can use that, the log score for this observation, the red line, would just be that d-norm function evaluated at where our observation location is passed in as the data to that function, and then the mean is going to be the kind of the optimum of either of these curves, and the standard error is going to be what's the spread of this distribution basically. So this approach is the log scoring approach I really like because it's incorporating both the prediction as well as the uncertainty. And it's really robust to a wide class of models beyond just the time series ones. And so again, it's really applicable to the whole family of distributions that you might run into with GLIMs and GAMs and things like that. So that is it. So we are about at time. I've got about 5 minutes. Is there any questions, comments, thoughts? Eli?
Yeah, I just had one comment about, to emphasize about doing cross-validation with time series data. So if you don't have time series data, then you just kind of leave one out, and the other points are not informing that point that you left out. But if you have a time series, then the